in power cycle, configuration. The Brighton cycle, being the idealized model for the gas turbine power plant, being the idealized model for the gas turbine has a reversible adiabatic compressor and isentropic. Reversible adiabatic means isentropic. And reversible adiabatic turbine. In the following examples, there is the following discussion. We are going to describe the Ericsson cycle. It is found that previously that the isothermal process would be preferable to the adiabatic process in both the compressor and turbine. The resultant cycle is called the Ericsson cycle. Consists of two reversible constant pressure consists of two reversible constant pressure process and two reversible constant temperature process. The reason the actual gas turbine does not attempt to emulate this cycle rather than the Brayton cycle is that the compressor and turbine process are both highly flow rate processes involving work-related devices in which it is not practical to attempt to transfer large quantities of heat. As a consequence, the process tends to be essentially adiabatic, so that this becomes the process in the model cycle. Adiabatic process for turbine and compressor. There is a modification of Brayton gas turbine cycles that tend to change its performance in direction of Ericsson cycles. In modifications of Brayton gas turbine cycle in direction of Ericsson cycle. We have two parts: multiple stage of compression with intercooling, multiple stage of expansion with reheat. Such a cycle with two stages of compression and expansion, and so incorporating a regenerator is shown in the picture 12.6 will be provided here. The air standard cycle given on the corresponding TS diagram, also in this picture. It may be shown that for this cycle, maximum efficiency obtained if the pressure ratios are if equal pressure ratios and maintained across the two compressors and two turbines. Maximum efficiency is obtained if equal pressure ratio are maintained across the two compressors and two turbines. These pressures for example P1 on P2 equals to P3 P4 maximum band T6 P6 on P7 P8 on P9. In this ideal cycle, temperature of air entering the first stage of compressing T1 shown here, and that temperature after heating and the temperature after reheating T8 is equal to the temperature in the first turbine T8 is equal to temperature in T8 equals to T6 T3 equals to T1. Furthermore, in the ideal cycle, it is assumed that the temperature of high pressure air leaving the regenerator T5 is equal to the temperature of low temperature air leaving the turbine, and T5 equals to T9. This temperature for ideal, we have a Q exchange T5 for ideal cycle. If a large number of compression and expansion stages are used, it is evident that the Ericsson cycle is approaching. That is shown separately in the next picture. In practice, the economical limit to the number of stages is usually 2 or 3. A turbine and compressor losses and pressure drops that have already been discussed would be involved in any actual unit employed this cycle. The turbine and compressor using the cycle can be utilizing a large number of the diagram shown the gas turbines many stages of approaches to the Ericsson cycle. The turbine and compressor using this cycle can be utilized in a variety of ways. Two possible arrangements for closed cycle are shown in the picture here. Closed open cycle arrangement of Ericsson, closed cycle, these are closed cycle Ericsson arrangement. One advantage frequently sought in a given arrangement is ease of control of unit under various loads. Detailed discussion of this point, however, is beyond the scope of this book. The next section is the air as standard cycle for jet propulsion.